participants and the audience, students, and some of my older students who are faculty as well in the other institutes. I can see some of the names here. So I hand over the session to you, Dr. Johan. So you can take us through for the behavior of retaining wall with relief shelves.
Thank you, sir, for having a nice introduction and for having me. Good morning, all students. As sir has informed me, he has already covered this earth pressure theories and all things. So he has invited me so that I can showcase my work, which is related with the retaining wall with relief shelves. So before proceeding through this thing, just I want to mention that why this relief shelf has been introduced and what is the purpose of introducing additional structural member into the conventional retaining wall. So what exactly is there that for construction of this rigid retaining wall, the important aspect is this magnitude of the earth pressure. Okay, so what dimensions of the retaining wall we look for, we were designed for, that is always depending upon the magnitude of the lateral earth pressure which is working on the wall. So the thing is that somehow if you can manage to mitigate this lateral earth pressure on wall, you can substantially reduce the cross-sectional dimension of your retaining wall, and that will be a good saving as well for that will good saving. So somehow there are so many mechanisms are available for reducing the lateral earth pressure on wall. So one very popular technique is that using some geo inclusion in terms of the EPS geofoam. You have heard of this thing, and where we introduce this EPS geofoam just behind the retaining wall and in between the retaining wall and backfill. Introduction of this geomaterial will reduce the lateral earth pressure substantially. However, there are some limitations are always there with any kind of this training. This first limitation is this is a costly affair, and second thing is that once this gets compressed, so the backfill settlement also get affected by this kind of settlement also. And what will be the actual efficiency of this thing, that depends on many factors. So that is also a crucial study, and fortunately I have done some kind of study on this thing. For moved on further to this particular thing, what another technique is your that introduction of relief shelf. So before knowing to this thing, I'll just introduce what exactly is the relief shelf. So relief shelves are horizontal platform which are monolithically constructed with the stem wall. These are perpendicular to the wall stem, and these are made as I mean these are extended into the backfill at right angle. Okay, so far the what we have noted, this is always done with the right angles. Somewhere I have seen they have suggesting, not we have seen any constructions here, then you can give some inclination to this particular relief shelf. So sometimes if you look for the literature, you may encounter this thing. So far the popular one is the with the right angle. So what we noted that in China, in this Haoye railway section, they have changed their design from conventional gravity wall to retaining wall with relief shell. And what they have noted that they could able to save good amount of engineering cost, construction period, as well as the excavation quantities. That is an appreciable amount. So, however, what lacuna we are facing is that we don't have any design guidelines to construct such walls. Okay, so finding this that we don't have any design guidelines, I chosen this topic as a my PhD work, and whatever I'm presenting over here is that either my PhD work or the post PhD work, and some sir has also asked me to include a case study. So at the end of this presentation, I'll include one case study which will be showing that how some wall has failed, and through the forensic analysis of this failed particular wall, what we have learned. Okay, so reaching to this thing. And during this search, I have also got to know the similar kind of wall, which is called as a gravity-locked wall. You can see that the horizontal platforms in the terms of relief shelf over there. The only thing is that the shape of this wall stem is not uniform, not a trapezoidal one. Here, this shape is getting changes. So lower sections are much thicker than the upper one. So that's why this is renamed as a gravity-locked wall. Some people who are constructing, they have patent over this technology, and this is being widely adopted in the various government projects also in the nearby areas of Pune as well as in the various districts of the Maharashtra. And recently I come to know that this particular thing has been adopted for a project which has been floated by NHAI. Now, so the very first literature we could get through this Ljungqvist, where he has proposed this kind of earth pressure distribution with the introduction of the relief shelf. So without having a relief shelf, the earth pressure distribution will be somewhat kind of this a triangular distribution. So once you introduce a horizontal platform over there, the Ljungqvist has suggested this this earth pressure distribution will be somewhat like a segmented triangular distribution below the relief shelf. However, once a charge is over there, that's how you can see that this is not starting zero from here, it's starting from zero from over here. So this has been termed in the equivalent, I mean the surcharge has been represented into the equivalent height of the backfill. Okay. So however, this proposal, I mean this theory was over there, but no background study was behind of this thing. So in earlier one other philosophy which was proposed by Tasagreli, who has also showed that this kind of retaining wall with relief shelf can be capable of any modification into the bending moment of overall bending moment distribution of the. However, one thing he has suggested that such wall will be working only when your backfill will be filled up in this manner. What he suggested that once relief shelf, I mean wall has been constructed, relief shelf has been properly monolithically constructed, and while backfilling, this particular thing will be having a void. Okay, so what he proposed that when this void will be existing, then only this kind of wall will be working. Okay, so however, with our studies, we have noted this is not true, and similarly. 1973 CRRI people have also given some proposal regarding this various kind of theories for the reduction of earth pressure. So if you can, if you are interested, you can look for this paper. Okay. So after noting these literature, what I have noted that this mechanism is really unavailable, which is explain this phenomenon. Okay, a many few, a few physical tests were reported through which we could notice that there is earth pressure reduction is happening, and effect of surcharge was never studied before, and there was no numerical model which was ascertaining this earth pressure distribution. So fortunately, fortunately, I am the one who has somehow started this numerical modeling kind of thing with this kind of wall. And absence of design details, as I mentioned in the very beginning of this literature. And what we noted that throughout this study, everybody was talking about the earth pressure distribution, but regarding the serviceability criterion, nobody was talking about. So serviceability criterion is much related with the backfill surface settlement as well as deflection of relief shelf. So that has been not explained earlier. So that have also included in my study. Now, so I have subdivided my overall analysis into the three segments, where one segment is related with the physical model test, another one is numerical analysis, and third part is some analytical model. So starting with the very first experimental evaluation, what I did this using a small scale model test of 0.6 meter height. I did some experiments, and what I got from there, I'll just show you. So I used a uniformly graded sand for this study, having this physical properties, and these are the frontal view of the wall. I'll just showing you because many interested students who are doing PhD and masters over there, they'll be using instrumentation also. So this is the front view of our model wall, where the earth pressure sensors were placed at the 6 different positions. And if you look at the side view, so this was the arrangement. We could introduce our relief shelf different position. So what we did that we made an arrangement over there that when we have to use a single model wall, we can introduce this kind of attachment over there. When we have to use the wall with relief shelf, using a nut and bolt system, we could fix this relief shelf over there. Now, these are the pictures you can see. So this is a half sand bed. This during the preparation of sand bed for this model test, you can see. So here, if you can see, this is a relief shelf over there. So this is looking like a sand. Why it is happening? Because what we did that for this relief shelf, we have pasted this with a We glued this surface of this relief shelf with sand over there, so that it can offer the friction. Okay, so at one other important thing is that because this is a plane strain condition we have to maintain, so at this end of this relief shelf we have also glued some what should I say, bentonite slurry we have introduced, so that no friction should be offered at this end of this relief shelf. So using this pluviator, which was developed in our lab, we just pluviated the sand, and at a desired density we prepared the sand bed, and for this prepared sand bed we have applied some load and noted down what earth pressure distribution we have done. So this is the arrangement you can see. So as in this particular study, our wall was non-yielding one, so that's why we have provided a mechanical jack over here, which is not letting the wall to move, and similarly some fixtures are available which is not letting move towards the backfill, neither away from the backfill. And using this LVDT we have also ensured that that wall has not moved. Okay, so these are this information. Using this kind of deposition density and height of fall, we could maintain a relative density of 80% for the prepared sand bed, and we have raised our surcharge loading from 0 to 50 kPa in the incremental load of 10 kPa. So this is complete details of this experimental setup, and you can have this pictorial view of experimental setup. And using this hydraulic jack, we could apply our loading as we wanted. Okay, so here is a picture of relief shelf. You can notice over there. Now some stiffeners are over there, just so that the this tank wall should not move laterally. That we have to take care. I'm not going into that one, but any interested student who is going for physical modeling, he can always write back to me. Okay, now this is the experimental test description, where we have introduced the various combinations of the relief shelf positions. Okay, positions as well as the width of the relief shelves. So using single relief shelves at various positions, 2 relief shelves as well as 3 relief shelves also. So out of this various experiments, what results we have got, I'll just illustrate you. So this is segmented into 2 parts, without relief shelf and with relief shelf. So here I'm able to show you what earth pressure distribution what we got without surcharge case. So if you can see, without surcharge, the earth pressure distribution was like to this one. So all these circles are showing the positions of the earth pressure sensors, where we have noted this our earth pressure reading, and we have directly connected with the lines, because we could not introduce many earth pressures very closely, because there are some limitations for the where interference of these earth pressure sensors will be happening. So that's why we have to keep them quite apart, so that they should give the proper reading. So that's why we have done for this 6 readings over there along this height of wall. So if you can see, what we noted in Jackie's earth pressure distribution is similar to this one at the rest condition, but what we got, this earth pressure distribution is similar to this one. And what we noted that another study by this Khosravi, he has also noted that similar kind of earth pressure distribution is happening. You can see there is earth pressure reduction is also happening at the bottom of this relief. So what exactly is happening? If you assume this is a wall, so at this corner some arching action is happening over there, and due to this a small reduction of earth pressure you can note at the bottom of relief shelf. So instead of going directly like this way, it has some action. So that is an important thing, and you can look for this paper where you will get the explanation of this thing. And once we introduce one relief shelf over here, so what we noted that below this relief shelf earth pressure has drastically reduced. So now this relief shelf width has been taken, and 3 configurations over there, where relief shelf position has been fixed, only the width has been changed. So once we keep on increasing the width, what we noted that with a smaller width, this much was the earth pressure distribution, and once keep on increasing, this earth pressure also got reduced. And you can see that there is a earth pressure distribution above relief shelf over here, a small triangular distribution you can see, and similarly below this relief shelf you can see another triangular distribution over here. So what exactly this relief shelf has done, has segmented the overall wall earth pressure distribution on wall into the 2 small triangular distribution, and that's how the reduction of the lateral earth pressure you can see. Okay, so if you want to get what will be the total earth pressure reduction, so what exactly you have to take the area of this curve. Okay, area of this curve on this axis, And for this relief shell case, you have to take the area under this curve, and here by subtraction you can get how much earth pressure you have reduced. And similarly for the various position, if you can see, then when once we moved on to the another position, what we got, this earth pressure distribution of relief shell with this one, and below this earth pressure distribution is similar to this one. So similarly, as noted, that increase in width of relief shell is also playing the part how this earth pressure distribution will be below this relief shell. So not only the position as well as the width of relief shell is also responsible for changing the earth pressure distribution below the relief shell. Okay. So similarly, once we placed our relief shell at a very bottom position, what we noted that this is not appreciable because the major portion of the earth pressure is lying in this portion. So why should go for placing a relief shell at very bottom? So we disregarded this idea that so this experiment was very much beneficial. So we could decide that where should be the position. So however, this experiment is not fruitful in terms of the reducing the earth pressure, but definitely this is really in helping to figure out where the position of relief shell should be. Okay. Now moving to the same experiment with the two relief shell, if you can see, what we noted that just in between the two relief shell, the pressure is almost negligible. Okay. However, once we place this relief shell a little bit lower position, what we noted here again a triangular distribution we can notice over here. So if you can see, as many as relief shells you are adding, a smaller, if you can see, three triangular distribution you can notice. Okay, one triangular distribution like this one triangular distribution like this one triangular distribution you can see over here. So instead of getting this much earth pressure distribution, you can see this is the earth pressure distribution you are getting with the introduction of relief shell. So what we noted that earth pressure distribution, total thrust reduction is the range, ranging between the around 73 to 79%. So what we noted that out of these findings, that placing a relief shell at a very bottom position is not beneficial, and placing a relief shell at a top, middle position, what we noted this is a beneficial when without having any surcharge condition. Okay. Moving with the same experiment with the surcharge, this is very interesting to note here there. Without having any relief shell, if you can see, the earth pressure distribution is like this one. What you study theoretically, this earth pressure distribution should be somewhat not like this one. This should have been like this one. Okay. So what exactly is there? Due to this application of surcharge, the lateral earth pressure distribution magnitude of this earth pressure is majorly higher in this portion, and this is lower in the bottom portion. This is why happening because this is mitigation of the lateral earth pressure. This earth pressure magnitude of earth pressure diminishes with this height, and that is why the effect of surcharge is not noted in the bottom position of this wall. However, this introduction of relief shell, what exactly it is really interesting to note. Instead of getting decreased unaffected in the upper position, what we noted that lateral earth pressure gets on increasing on the upper part of wall. Okay, and this is happening because a stiff member, because this was stainless steel was there, so a stiff member has been introduced over there, and once the application of surcharge is over there, this stiffened member is taking care of this whatever load is over there and not letting to pass the whatever is applied from the top. And once this is taking the load, so overall overburden pressure is increasing into the upper this area, and lateral earth pressure is somehow directly proportional to the overburden, and which is why this earth pressure, lateral earth pressure has been increased into the upper portion. Okay, and similar noting we have also noted down. So once we keep on increasing the width of relief shell, this lateral earth pressure has been increased drastically. So now it is really very important to know what should be the optimum width. Okay, if you introduce a very wider relief shell in case of surcharge loading, what will exactly will be happening is that in here the earth pressure will be very much high. Okay, this if you count the overall earth pressure distribution, overall lateral earth pressure, what you noted that here it will be increased and here it will be reduced. So however, this values are very much small already without the relief shell, if you can note. So the appreciable amount of reduction will be very much lower, because if this value keeps on increasing, this will be not mitigating, this will be keep on increasing. So that's why crucial point is that width of relief shelf. Okay. Now, once we change this position at a middle position, what we noted as increase in earth pressure is not as much as it was noted in when relief shelf was closely placed to the uh, surcharge. Okay, so what we noted that we should place our backfill, relief shelf at a middle position so that we can offer some reduction in the bottom portion and also doesn't allow the earth pressure to increase. Okay, and with the other combination, if you can see, the similar distribution is also happening. The interesting part is with the two relief shelves. Okay, so now if you can see with the two relief shelf, when we are using two relief shelves having a smaller width, what we noted there is hardly any changes are happening. However, once we use a wider relief shelves, two closely placed wider relief shelf, what we noted this shadowing effect is happening. Okay, and shadowing effect is that you can see that whatever surcharge has been applied over there, that has not been completely reached to this position due to this provision of wider relief shelves. Okay, and that is why this lateral earth pressure in this particular section has not been changed much. Okay, now moving to next slide. Yeah, so when the same two relief shelves were widely placed, okay, you can see the earth pressure is also changing. So here you can appreciate the shadowing effect due to the closely spaced two relief shelves. Okay, now moving to another one more important thing is also I have to tell you what exactly is there is happening. There is a superposition of two simultaneous phenomena happening. So what exactly is happening that with the introduction of this relief shelf, this relief shelf here in this portion, provision of this relief shelf is not letting the surcharge to surcharge to get introduced over there, and also the provision of this relief shelf is also increasing the overburden in this section, because whatever this cannot completely subsidize the applied surcharge. Some portion of surcharge will be definitely going to this thing. So this particular relief shelf is helping to, lower relief shelf is helping to increase the overburden, and upper relief shelf is helping to mitigate the overburden pressure. Okay, so somehow the combination of these two things are happening over there, which is responsible for whatever the lateral earth pressure you are witnessing over here. Okay, so another important thing is there that all these relief shelves were perfectly glued with the sand what we were using in our sand bed. So these are offering also friction to nearby areas, and that is also responsible for the changing the lateral earth pressure distribution in the surrounding areas. If you can see this particular EPC, if you can see earth pressure sensor is placed just below the relief shelf. Okay, so at a very smaller and very small magnitude of the surcharge, earth pressure is almost zero. But with the increase in surcharge, this value is appreciably higher. Okay, so this is another finding for the two relief shelf. So from summarizing all this what we got, we noted that using two relief shelves, what we got is a best optimum positions where we can get appreciable amount of total lateral thrust reduction in the range of somewhat 60%, and even with the higher amount of surcharge, which is 50 kPa, we could noted that this is ranging 40 to 50%. And in a single relief shelf case, we could notice that this is ranging between 23 to 40%. So from this model test, we have recommended that using the two relief shelves is always preferable. Okay, now, so this part I was introduced over there to summarize all these things, but I have already discussed in all things, so that's I am just skipping this part. Okay, now not only this telling this what we got from this model test is not important, because this is a small scale model test, so we should definitely have some ethical formulation, because this will facilitate any designer that how should bending moment and shear force distribution should be known to the wall for this kind of wall. So what we thought that we should introduce some analytical model that will be able to propose what should be the optimum width of relief shelf, position of relief shelf, as well as what will be the distribution of the bending moment, shear force, which is very much required for the reinforcement detailing and the design of retaining walls. So yeah, assumptions are always very much important. So these are very simple assumptions we have considered, that during this movement of this wall at a junction of wall stem and relief shell, this will be 90 degrees throughout the all movement, and effect of the axial force on the bending has been ignored. Why this if axial force has been introduced over there, I'll be discussing this part. And what we have assumed that what earlier theories were there regarding the earth pressure distribution, we have assumed that same earth pressure distribution is working along the wall with relief shell, and using that particular thing, we have introduced some experiment, some analytical formulation. So now one important thing is that this particular thing is where earth pressure distribution is not a continuous, because it is getting changes. So this is a discontinuous function. So in order to make this discontinuous function into a simple mathematical expression, we have used this Macaulay's function. You must have studied in class 11th standard. Okay, so this is force diagram of the retaining wall with relief shell we have considered for the analysis. So if you can see here on the wall stem, you can see this kind of earth pressure distribution is working, and along with this one, due to this introduction of relief shell, whatever the backfill weight is over there, that is being supported by this relief shell, and due to this loading, this kind of equivalent force diagram you can see. Okay, over there, one moment will be working over there, one shear force is working over there, and due to this weight of backfill, it is supporting axial load you can assume at a midpoint of the relief shell. Okay. Now, I'm not going into the mathematics. Only what we did, we consider this as a beam, and using this analytical modeling, what you used as a theory of bending. So loading conditions, we are very much aware. Boundary conditions, we are very much aware. So boundary condition is this wall is fixed at the bottom and free at the end. So considering this boundary condition, we have used the theory of bending, and once the loading condition is very much known, we have just keep on integrating. So once with the one integration, we got the shear force, and with the one more integration, we got the bending moment, and finally with the integration of one more time, we got this wall deflection. So this was introduced with the Macaulay's function, and with the integration, what we got this kind of expression. So I'm not going to elaborate. Anybody who is interested, he can look for the paper. I'll be giving you the link of all those paper at the end of this presentation. So what interesting thing you can notice over there, that without relief shells, your expression will be look like this one. Okay, so this is expression for the loading, this is for shear force, this is bending moment, and this is for the wall deflection. So moving towards the shear force distribution, if you see, without the relief shells, shear force distribution will be like this one, where this K is your K Q naught X plus gamma K X square by 2. So quickly wrapping this thing, K is your lateral earth pressure coefficient, and Q naught is your surcharge pressure, and X is the position you are considering at any wall section, noting and measuring from the backfill surface. So with this introduction of relief shell, you can see this expression has been introduced over here and having a negative sign. So if you can see, clearly see that relief shell introduction has reduced the relief shell, okay, by this term. And similarly, in the case of bending moment, you can see the bending moment expressions are, you can see -1, and this positive term has been introduced. So with this amount, bending moment has been also reduced at any section. So all these expressions are giving you at any sections. Okay, similarly for the wall deflection also. Okay, now there is one very much important thing which is related with this thing. I just want to again brief you this thing. What tendency will be having this wall is there, if you having considering this particular point, what will be having, this load is working on this particular relief shell, and a lateral load is working on this wall section. Okay, if you don't balance it properly, what will be having, if you keep on increasing the width of relief shell, what will be happening is there, the backfill weight of the backfill supported by the relief shell will be very much high, and there will be a situation where this will be having a tendency to make the wall instead of moving away from the backfill, it will be having a tendency to move towards the backfill. So that there is a need that where we must be aware of that that what would be the critical width of the relief shell. So for deciding the critical width of relief shell, another radical model has been proposed, which is simple free body, I mean, which is completely based upon the free body diagram of force, I mean, free body diagram of this particular wall at different sections. So what we have done, we have taken 3 sections at every junction, and we have drawn the force body diagram. So quickly wrapping this thing, if you can see, this is all these values are coming from the lateral earth pressure, and this value is coming due to the weight supported by the backfill, and we are making an equilibrium equation at this particular position, and these are the lever arms you can see. And once you write an equilibrium equation at this position, you will get this expression, and reaching to the Lipton position when moment at this section will be 0. This will be giving you the what will be the limiting width of the relief shell L1. Okay, and using the same free body diagram at different section, you can land to these expression. Now, important thing is there, if you go for this particular thing, what exactly is there? If you look at that is crucial. What exactly is there, that this particular relief shell will be taking care of the soil column above it. Okay, but in case of this lower relief shell, this will be taking the weight of the backfill, which is lying over here, and difference of this one over here, if you can see, this soil column, weight of this soil column will also be supported by this relief shell. Okay, and which is why, if you can see, this particular additional load is over there. Okay, and if you introduce into the expression, you will be it will be interesting to know that the second, I mean, critical width of the second relief shell is always depending upon the width of the first relief shell. So what we noted, that this particular limiting width of the relief shell, which is independent of the density of backfill you are using, this is function of the square root of the lateral earth pressure. And third thing is, this is depending upon the back relief shell, which is lying above this relief shell. So there is a generalized expression has been also proposed over there. Now, through the parametric study, some interesting things we noted down. So for a 6-meter height of wall, we have introduced the 3 relief shells of varying width. And what we noted, that without relief shell, this is the distribution of the shear force diagram. Okay, but with the introduction of relief shell, we noted that shear force has reduced drastically. Okay, and here you can see there is a change in the profile, I mean, curvature is over there. If you can see, there is a change in the curvature over there. This is showing you the position of relief shell. Okay, that's what exactly happening over there. And what we noted, that with the change of the width of relief shell, there is no change in the shear force. Okay, only the position of the relief shell is responsible for changing the changing the shear force diagram. Okay, that is based upon this proposed model. Okay, however, in case of bending moment, what we noted, once we keep on increasing the width of relief shell, what we noted, that bending moment has been not only reduced, I mean, drastically it has been reduced, and it has been ranging that 66 to 86% what we noted from the parameter study. If you can see, wherever this kink, you can see what exactly is happening. Above the wall, I mean, if you talk about the relief shell, if you keep on increasing what width of relief shell, it will be supporting a higher amount of weight of the backfill, and it will be having a tendency to move the wall towards the backfill. So that is what is making to reduce the moment at the wall section. Okay, now, and due to this kind of phenomenon we have witnessed in it, there will be also in the reduction in the wall movement. So this is without this relief shell, and this is with the relief shell, you can see. So good amount of wall reduction you can see. So that is also a crucial point, because whenever we design the wall, we have to take care that wall should not move very much away from the backfill, because this will leading to the excessive backfill surface settlement, and this will be dangerous for a situation where the supporting structure which are nearby this backfill, this will be having some distraction is over there. Okay, moving to this another point. So we have also done analysis over there. What we noted, that for the 6-meter height of wall, we have calculated and noted that this much amount of saving we can note down. So what we noted that concrete we can save 37% and steel 17%, and the overall cost we can save up to the 32%. So for a typical 6-meter height of wall, I have provided this complete detailing in one of my published paper. I'll be giving you this link. So based upon this particular paper, we noted that 30% saving is a good amount. So moving to another analytical model, I'm not going to this much again. This one, I'll just show you what exactly interesting thing what we found, that we have given that how the lactive earth pressure distribution will be varying due to the introduction of relief shelf. So this particular analytical model was proposed for a wall with having a single relief shelf, and only assumption we are involving that wherever this relief shelf will be placed, this will be having a width such that it will be touching the shear failure which is generated behind the retaining wall. Only this is the crucial assumption we have considered. Okay, so coming to all the derivations and what we got, the interesting thing you can note it down that without the relief shelf, total lateral earth pressure you can note it down is here. However, with the introduction of relief shelf, this total thrust reduction is having this much expression. Here you can see the crucial point is the H by H. H by H is the position of relief shelf. I mean, this H is the giving you the position of relief shelf from the backfill surface. So the important parameter which is governing your overall lateral earth pressure distribution is your H by H. Okay, and similarly the bending moment is also the function of this position of relief shelf. Now, there is one interesting part is I have noted that not only the total lateral earth pressure is getting introduced, also there is shift in the overall point of location of this total thrust. What exactly is happening that once this earth pressure distribution is getting changes, so without this relief shelf, what we noted, this is the point of application of the total thrust. However, with the introduction of relief shelf for the same wall, this is the location of the point of application of the total thrust. So what we noted that while you will be designing this thing, you will be always looking for what is the maximum bending moment. Okay, so what maximum bending moment you can get, what will be the total thrust and where it is working over there. So from this bottom you will get this moment of this particular force working over there. So once this quantity has been reduced, so maximum bending moment will be also reduced. So corresponding to this maximum bending moment, you introduce the amount of the reinforcement. Okay, now so based upon the parametric studies, what we have noted down, what we noted down that maximum reduction we can get in the range of nearly 50%. Okay, and the maximum bending moment reduction we can get something like 40 to 44 to 46%. Okay, so moving to, I mean, this is there are a big number of tables are over there. I'm just giving you what exactly is happening over there. However, what we noted interesting point is there, this particular reduction in the maximum bending moment and total lateral earth pressure reduction is also depending on the phi value and the interface friction angle of the soil and wall also. So this is a wide ranging study, and what we noted has been, so quickly wrapping what we discussed over there, that relief shelf reduces the bending moment, shear force, and as well as the wall deflection. So from the static force analysis, we could able to give you the maximum allowable width of relief shelf. If you provide relief shelf more than the allowable width of relief shelf, definitely it will be having a tendency to moving the wall into the backfill. Okay, so shear force is a function of your position of relief shelf, and the bending moment is not only the position as well as the width of relief shelf also. Okay, another points are I have already cited already. Okay, now from the parametric study that I have shown as very small part, that was interesting to note over there. So what we noted that width of relief shelf is function of the friction angle of the backfill, and whenever this friction, I mean, you are using a higher friction angle, I mean, you are using a backfill having a higher friction angle, you require a lesser width of relief shelf. That what we noted. And for a given phi, of the backfill, what we noted that B by H, that is your normalized width of relief shell, that is inversely proportional to the position of relief shell. Okay, so what we noted that maximum thrust reduction we can get in the range of 50%, and for a given phi value, thrust reduction is inversely proportional to the interface angle of the backfill as well as the wall. Okay. Other points are general points and not very. This is, I mean, limited to the particular parameter study. Okay. Now, moving to the assessment using this numerical modeling part, and what we have done, two parts with the having surcharge and without having surcharge. So I'm showing you with having surcharge only. Okay, without having surcharge was not something kind of beneficial over there. So that's why I am not introducing. However, you can refer this always. Yeah. So doing this part for the static surcharge, what I did that using a parameter study on a wall having for 8-meter high wall. What I did is that I considered three configuration where position of relief shelf has been changed, as well as the width of relief shelf has been changed, with the number of relief shelf has also been changed. So using a single relief shelf, three positions have been considered with this much width of factor. So width factor is just normalized width of relief shelf, and position factor is your normalized position of the relief shelf, where this small h is giving you the position of relief shelf and this capital H is the height of relief shelf, because we will be using this term very frequently during this discussion of research. That's why I have to tell you this thing. And with the 2 relief shell combination and 3 relief shell combination, these are the position factors as well as the width factor. Okay, so overall, I mean, throughout this study, we have applied the 50 kPa surcharge, and this surcharge was not exactly placed near the wall. This surcharge was placed somewhat h by 16 distance from the edge of this wall, because we always prefer so that any surcharge should not be very much near to the wall. Even during the compaction of this backfill, we always keep a safe distance through it. Your roller is allowed to compact this wall, and during this, very close proximity of the wall, we always prefer manual compaction. Okay, so considering that point, we have placed our surcharge a few distance away from the wall stem. Okay, these are the parameters I have considered for this thing, and this was a quite well validated model. So quickly moving towards the results, what we got using a single relief shelf at different position, what we noted that with the introduction of single relief shelf, this is marginally altering the earth pressure distribution just below the relief shelf only. Okay, above the relief shelf, this black line, if you can see, this is the without the relief shelf, and having the with relief shelf, this is marginally decreasing in this at this position, and upper this is quite similar to the what we noted. Only the thing what we noted, because we have considered a rough condition of this relief shelf also, so that's why this reduction may be due to this one thing. Okay, so what we noted, that introduction of single relief shelf is not much altering at any position. So nearby relief shelf, this is happening, and one important thing is there, because due to the surcharge loading, relief shelf having a tendency to move to deflect. So due to this deflection, arching action may also occur over here, and at these position, this much earth pressure reduction you can witness may be due to the arching only. Okay, so what we noted, that this can hardly alter any earth pressure distribution other section except the nearby locations of the relief shelves. Okay, so placing a relief shelf at a very bottom location is always not preferable. This is very similar to the what we noted from the our physical model test. And once we noted down this single relief shelf is not noteworthy in giving the reduction in the lateral thrust, we move for the 2 relief shelf combination at various position. What we noted over there, that you can see what shadowing effect I have discussed earlier. This was again witnessed over here. Okay, once you are using appropriate width of relief shell over there, we can notice that reduction in the lateral earth pressure is much greater than the case of other positions. I mean other combination of the relief shell. So what is over here there, that positions are completely fixed. Only thing is that we have increased the width of relief shell. So that's why you can see the shadowing effect is happening, and that's why we are witnessing the good amount of earth pressure reduction in this section of wall. Okay, so now another important thing what we noted is there is change in the backfill surface settlement will always be occurring whenever relief shelves are introduced over there. So what we noted, if you can see this black line, if you can see, this is hard to visible, but this was the backfill surface settlement profile. However, once you introduce a relief shelf over there, what happened is there that due to this introduction of relief shelf, because a stiff member is over there, this is not letting the soil to move downward, and that is why the relief, I mean backfill surface settlement near the wall is lower compared to a wall without having any relief shell. But once you keep on increasing the width of relief shell, what is happened, noted the down, that this backfill settlement keep on increasing. Why it is happening? Because if you keep on increasing the relief shelves, what will be, this will be having a close proximity to the applied surcharge, and this will taking a greater part of surcharge, and if it will be supporting greater part of surcharge, it will be having a tendency to deflect, and once it will be deflecting, this will be leading to a deflection of the soil particles which are residing above this one. So that's why after appropriate width, this is again participating into the substantial amount of the backfill surface settlement near the wall. However, in all cases, we have noted down that after a certain distance, this is similar to the without relief shell case. Okay, so what we noted that although the two relief shell was able to reduce the lateral earth total thrust on the wall, but this was not appreciable. So what we thought that we will be introducing one more additional relief shell. At given this position, we have just keep on increasing the width of relief shell, and what are the findings are over there you can see. So with the smaller width of relief shell near in the nearby location, we could witness the reduction in the lateral earth pressure. However, here you can see increase in the earth pressure we can also. So if we keep on increasing, you can see the earth pressure in the upper part of wall is also introduced. Okay, has also increased, and this is similar to the physical model test finding. So whatever what we got over here is similar to the physical model test, and that is a point of satisfaction for us for both kind of studies, that this is matching with the physical model test. And sometimes while apart from this discussion, once we are doing your any PhD, you will be always having a tendency so that your results should be somehow confirmation from the numerical model test or the physical model test. Okay, so all the students who are there, that should also take care of this point, that whenever if you are doing this physical model test, you should also try to validate your result with the numerical model test, and similarly vice versa also. So with the introduction of higher width of relief shell, although the thrust, I mean lateral earth pressure has been increased, but the reduction in these portions have introduced overall earth pressure reduction into the wall. So if you can note down what we noted is this much amount of 26% of earth pressure reduction we can introduce with the having a relief shell width ratio of having 0.65. Okay. Now another thing, this backfill surface settlement, this is the similar pattern what we noted in the two relief shells case. Now an interesting thing, if you can see, because this wall was non-yielding one, major settlement vertical deflection, major vertical deflection of relief shell we noted in the uppermost relief shell, and once we move on, I mean once we keep on going downwards, we noted that deflection of relief shell is somewhat lesser compared to the relief shell which are placed on the topmost position. Why I am highlighting this point? Because this will be just opposite to the other finding, I will be discussing why this is important. Okay. Now, so all these points, I mean, we have summed up that what kind of ranges we have used and what percentage of earth pressure reduction we have noted down. So already I have shown you, that's why I'm not skipping this part. Okay. Now, another important is thing that this is my post PhD work where I have conducted some limit analysis for this kind of wall, which is subjected to some static surcharge loading. So I use this Optum G2 model, Optum G2 computational software for modeling this kind of wall. So where 10-meter height of wall with the various combination of relief shelves, and what I have done is that I have applied some uniformly distributed surcharge, okay, and this particular surcharge was kept on increasing until the failure of wall, okay. So whatever amount of surcharge at which this particular wall gets failed, we have defined this as a collapse surcharge or collapse surcharge, okay, and we have monitored this collapse surcharge for the case of without relief shelf and with relief shelf, and the ratio of this thing has been introduced as a stability number, okay. So once I'll be discussing, it will be more clear to you. So collapse multiplier load is the again briefing this thing. Collapse multiplier load is the load at which particular this wall is getting failed, okay. So various combination of this position of relief shelf as well as the width of relief shelf, what we noted down, that once we keep on the width of relief shelf, this collapsible surcharge keeps on increasing, okay. Now another important thing what we noted from this, so this plastic multiplier of a shear strain we noted down, this always helped to get what was the shear failure plane or the mode of failure you can witness over there. So what we noted that without relief shelf, this was the shear failure plane. So if you can refer good books, you can see there are two potential failure planes in the case of cantilever retaining wall. One is having this much inclination and one is having this kind of inclination, and this orientation is completely depending upon the phi value, depending upon the width of this heel slab, okay. So this particular failure plane, whether it will be intersecting this wall stem, this is depending upon the various factors. So at this end of this presentation, I'll give you this book name where this kind of discussion is over there. So once I introduced relief shell, what we noted down that this particular failure plane has been intersected by this relief shell, and it has altered the failure plane also, okay. If you keep on increasing the width of relief shell, instead of going a failure plane like this one, it has a failure plane like this one, and due to this one, because a higher amount of soil is participating into the failure, that is why it has been having a higher capacity to take more loads on such kind of walls, okay. And similarly for the different positions, you can see on position and width of relief, this failure plane is also getting changed, okay. So then when the bottommost relief shelf, you can see bottommost relief shelf. So when your relief shelves are not having sufficient width, okay, this is not going to alter the shape of this failure plane, okay. Once only this touches the relief shelf, this will be trying to show its effect on the failure plane, okay. And similarly, this is findings what we noted for the various case of two relief shelf, okay. So again, these are the pictures for the two relief shelves case. So I'm quickly skipping these things, okay. Now, so interesting thing what we noted in the three case, just it's keep on increasing with the width of relief shell. So if now the important thing is that you see so when we noted down that when keep on increasing the width of relief shell and it is not giving you good amount of collapsible load, why should not use a single relief shell? So it was very much interesting that even with the use of three relief shell, single relief shell was sufficient to increase the collapsible multiplier load for such kind of wall, okay. So with the three relief shell, this is the orientation of failure plane patterns, okay. Now the stability number, this has been defined as the ratio of the multiplier load with the relief shell and without relief shell. So what we noted that beyond a B by H value, there is no change in the stability factor, Okay, so this value was given as a optimum number for deciding that what would be the width of relief shell. So we noted that B by H is equal to 0.5 will be the appropriate width for the single relief shell. Okay, now so once again we find out that 3 relief shelves and 2 relief shelves are not giving a sufficient amount of improvement in the load capacity or load taking capacity of such kind of wall. We have again back to the move to the our single relief shelf wall study and varying the again position and width. What we noted down that topmost position having the B by H is equal to 0.3. If you keep on increasing the width of relief shell, this will be going to alter your shear failure plane of this kind of wall. If you can see, witness over here, once we keep on increasing this wall, instead of having this much kind of failure plane, this will having this kind of failure plane. Here, this kind of curvature is also taking. Another important thing is you can see notice there the below the your base slab, this failure plane is also going to be changed. So here this much mass is taking part into the failure of this wall. That's why which is I mean with the further increase of this width relief shell, instead of this wall is getting failed, this particular having a tendency to get this particular a kind of slope failure. Okay, so this here this wall is not getting failed. I mean once keep on increasing the load and this wall is not getting overall slope is getting failed over there. That what we noted. So this is a important point to note down that I'll be discussing in next slide. Now what I was introducing earlier that knowing the critical width of relief shelf is very much important because the width of relief shelf is also playing into the behavior of the wall movement. Okay, so what exactly is that without having any kind of relief shelf, the wall movement has having a tendency and this was away from the backfill. And if you can see this base slab is having a movement kind of this. So once you introduce a relief shelf, and on the same scale all these pictures have been drawn, this will having a lesser tendency to move away from the backfill. And once we keep on increasing the relief shell, you can see so this wall is having a tendency not much going away from the backfill. Okay, you can see. And once we keep on increasing this thing, you can note it down that this particular wall has not having any tendency to rotate. This particular wall has only just slided. So here this B by having alpha is equal to 0.3 and B by B value of 0.5. This is having a tendency to slide only. That means this particular width is just sufficient so that this will not having a tendency to move, I mean not to rotate this thing. So this is giving you a condition where your moments have been equilibrated and only this lateral force is working, which is moving the wall only slide position. And once I keep on increasing the width of relief shell, what I have noted, this particular wall has a tendency to move into the backfill. Another interesting point to note it down that without relief shell, this particular wall, I mean this particular backfill settlement, if you can see having this kind of trend over here. And but if you keep on increasing the width of relief shell, you can see here is a horizontal backfill surface. I mean you can see horizontal backfill profile over there. And the due to this introduction, this settlement you can see is much far away from the wall stem. Okay, so this is always crucial whenever you are constructing any kind of structure in nearby the backfill. So suppose if load is applied and if your pavement is over there, okay, so you can consider as a traffic loading. I mean static traffic loading. Traffic loading you cannot say exactly because a static surcharge has been assumed. So if any kind of static loading if you assume over there due to the foundation of any kind of structure, and if this wall moves away, this will be again dangerous. I mean this will be again not preferable for making any kind of foundation over here. But with the introduction of relief shell, you can also utilize this particular space also. Okay, now another another important thing is there that this is always changing the failure plane angle. So without relief shell, we can note down that whatever failure plane we noted with the horizontal, this has an angle of 72 degree, and with the introduction of relief shell, this keeps on decreasing with the horizontal. If you can see with the relief shell, what we noted down that after width of relief shell, this doesn't change it. So what we noted down that optimum width again of beta is equal to 0.5, this angle is not going to be changed. This is noted down with 52 degree. Another important thing is that due to this kind of wall movement, there is a I mean, what we noted this from the vector movement of the soil surrounding this wall. There is an influence up to a depth of 3.87 without relief shell case. Okay, but what we noted down that with relief shell case, there is a wall movement soil movement was noted down in the case of 6.81 meter. Okay, and this is why which is happening because this is taking the higher amount of load, and due to which this soil movement we can notice up to a higher depth. Okay, so all things what I have noted down from my study, I have already cited one. So this is summary of all what we noted. So moving to the last part of this particular today's talk, this is a case study of a failed retaining wall. So this particular I'll just show you the wall and then we'll move to discussion of this wall. This particular wall was made in the Hyderabad, and this has failed after the monsoon. Okay, so what exactly the situation was there? This wall having a height of 10 to 13 meter. Okay, varying along length, where 20 meter part of the wall has been completely distressed, and this has collapsed completely, and which has led us to the forensic investigation of such kind of wall. So some pictures of wall I'm just showing you. You can see over there, there is a crack which has been introduced over there, and you can see some portions over the where backfill might not be very well compacted. I'm not pretty sure because this picture was taken once wall has failed. So due to the failure of this particular wall, this may have introduced or might be the compaction was not done properly. If you look at the one more picture over there, you can see this wall has completely cracked at a junction of wall and relief shell stem. You can see witness over there. Okay. So salient features, what we noted down that after few years of construction, a portion of retaining wall of 20 meter length has completely collapsed, and 20 meter length has been severely distressed. And the backfill which was used for the backfilling of this wall was loose to medium dense soil, and a very renowned professor was involved in this post-failure investigation. I cannot take his name over here, but from his report, what we noted that quality of concrete used in the construction was satisfactory, and construction joint were intact. Okay, so crack due to the failure had propagated almost up to the full thickness of reinforced concrete wall. So because the quality of construction was okay and everything was okay, so the important consideration we have to take care whether the design was done appropriately or not. Okay, so please have a look of this sectional dimension of this particular kind of wall which was constructed over here. So if you can see that base width was very much small. Okay, this is very much true that with the introduction of relief shell, you can save into the base width, but somehow this particular base width is about very much lesser as it should be. And however, we have noted down that they have used 5 relief shell for a 13 meter height of relief shell, and ranging from a width of relief shell of 2 meter to 2.5 meter. Okay, and also they have varied the thickness of relief shell ranging 0.3 meter to 0.5 meter also. So because we didn't have any kind of soil property, so we have considered a suitable backfill properties for the analysis of such kind of wall. And I have simulated this particular wall into the flat 3D, and what I have noted, this is somewhat really very much interesting. Okay, what I have noted is that at this particular section of wall, below a relief shell, tensile stresses has been generated, and on this section a compressive stresses has been generated. Now why this is interesting, if you go for a movement of wall, when wall will be moving away from the backfill, if section is moving, this section will be having a compressive stresses, and this section will be having a tensile stresses. Okay, so the wall face which is towards the backfill will be having uh, tensile, and which is non-backfill side will be having compressive. However, here is a stress reversal phenomenon has happened, and this is always happened due to the very wider relief shell of this they have used. Because what happened, they have used a very wide relief shell, and which has created a moment such that it has a tendency to move towards the backfill, and due to this very much high stress, this stress reversal phenomenon I could witness. Okay, so you can see the tensile stresses and compressive stresses with the magnitude of the 7 MPa. Okay, so what is written over there, that I have already briefed you. Okay, so what we thought, that why should not give a solution for this kind of wall. So our outcome is based upon the whatever analysis we have proposed, we have discussed. So we have designed, not designed, we have, yeah, we can see that we have designed this particular wall and noted down that in sliding and overturning, we have considered, I mean, we have got that factor of safety is well within the recommended limit. And with the use of flat 3D, what the earth pressure distribution, what we have noted down is this way. So you can see that this earth pressure distribution is somewhat different what we noted from in our earlier cases. One point has to mention that earlier cases this wall was non-yielding wall, and here this particular thing is a yielding wall. Okay. Now, important thing, you can see that contact pressure at base has also changed. So if you can witness this black line, this is contact pressure at base slab without relief shell, and with the introduction of relief shell, even the base pressure below the base pressure has also reduced, even the marginally, but this was reduced. Okay, so this is also leading a situation where you can reduce the size of your base slab. And also what we noted, with the introduction of relief shell, the lateral displacement of the wall has drastically reduced. So without the relief shell, this wall movement was similar like to this one, and with the introduction of relief shell, what we noted that this was the wall movement. Okay, this is really very interesting. However, the backfill settlement near to the wall was very much higher, and with once we move away from the wall stem, what we noted, this backfill settlement keeps on decreasing. Okay, but here with the introduction of relief shell, what happened is there that always backfill surface settlement was lesser than the wall without relief shell. Why it is happening is there, because this once this wall is moving away from the backfill. Okay, suppose this wall is moving away from the backfill which has no relief shell, the gap which is creating over there will lead to the settle the soil particles downward, and which is giving you this kind of backfill surface settlement. However, once you introduce a relief shell at this location and wall is moving away this particular relief shell will not letting the wall soil particles as much as which was in case of without relief shell, and that is why the backfill surface settlement near the wall in case of with relief shell is lower without the relief shell case. Okay. Now, and similarly, the backfill along with the backfill settlement, we have noted that vertical deflection of the relief shell, and what we noted down in case of yielding wall, the relief shell which in the topmost position has a smaller reduction compared to the relief shell which are placed at the bottom sections. Okay, so total thrust reduction we could witness that this was ranging somewhat 43 to 47%. However, we have to take care of this serviceability criterion where our backfill settlement should not be very much higher. So depending upon this thing, we have recommended the B by H value of 0.55, that is giving you a relief shell width having 1.2 meter. Okay, now from our analytical model, we have also proposed some solution, and we have noted down with this recommended width of relief shelf. The maximum reduction in the bending moment is ranging 77 to 85%, and shear force reduction is 77 to 88%. However, there is one important thing I have to introduce you, that we have considered two K values. Why it is happening? Because this is a crucial point, because we are not knowing that how much wall will be moving. If we take lateral earth pressure coefficient depending upon the what value of phi, that value is giving our K value is 0.27. However, what we did based upon the wall movement, we have normalized this thing, and we have calibrated the wall deflection, and according to the wall deflection, we have got that corresponding to the wall deflection, what appropriate K value will be there, and considering that thing, we got that K value of 0.4 only, and using both two things, we have compared this thing. So this is a comparison of bending moment, and similarly for the shear force. So excuse me, because I said this is shear force. This is both are bending moment at different K values, and similarly these are the shear force at different K values, and similarly for the deflection. So this is really very appreciable amount of saving in terms of bending moment. Now, what based upon our analytical solution, we have proposed this kind of configuration for this kind of wall. Another thing is that again, a static force analysis, we have introduced that what will be the optimum width. Okay, so that we have to take care that this wall should not move into the vacuum. Okay, so I'm quickly wrapping this thing. Based upon this much force body diagram, we have used our introduced method, and we have equilibrated that force which is working at every junction. So if you consider this junction, there is two kind of forces which is working over there. Is one weight of the backfill, and what second is your lateral earth pressure on the wall. Okay, so just equilibrating this at every corner, we wrote this expression for every junction, and what we got is over there is shown below. So I'm not going into the mathematics because this is very simple. You just note down all the forces and just make an equilibrium equation, and based upon this equilibrium, you can calculate what will be the width of relief shelf at every junction. Okay, so what I have got, I'll just quickly show you that B1, B2, B3 values. This much we noted down. The B1 is equal to 2 meter for the upper two walls, and other bottom three walls, the recommended width very well 2.5 meter. Okay, so so what we noted that all depending upon all these three, clubbing all these kind of models, what we suggested that instead of going a very higher width of relief shelf, we should use this much configuration. B1 is giving you the topmost width of relief shelf, and similarly once you move down, this is the recommended width of relief shelf. Okay, and however, what we noted in the failed wall, this much width was provided. So you can see all these three, all these four cases, you can see this is much higher than the limiting value of the width of relief shelf. However, in this case, limiting width is 2.8 meter, and they have provided 2.5 meter. So all these higher width of relief shelf has led the wall to fail. Okay, so this is a comparison of what they have designed and what we are proposing. Okay, here I'm concluding all these sum up of this thing, that most effective width of no. Just excuse me this slide. Please skip this slide, because this is not relevant to the what I have discussed just thing. So this is very much relevant to the what I have got with the K values. Okay, so based on this static force analysis, what I suggest that this particular width of relief shelf, what we have proposed over there, that should always be taken care into the consideration, whatever the earth pressure distribution your models are giving, because whenever you are doing this limit analysis, earth pressure distribution behind the wall, they are giving you only this what is the earth pressure distribution. They are not taking care of how the movement of this wall is happening. So the movement of wall as well as the earth pressure distribution, that should always be clubbed for a appropriate design of such kind of wall. Okay. So my final words are there that This is already established that wider relief shelves have a tendency to move the wall stem towards the backfill due to the weight of soil supported by relief shelf. So direction of force on the wall might have introduced the hysteresis reversal phenomenon due to the face of a stem, which has led the failure of all wall. And it is interesting to note that this particular thing has not been resolved, this thing, because this is a disputable manner disputable matter between the one who was constructed and one who has designed this particular thing of wall. So I have not submitted my report to them, but however, my paper has been published, and if luckily they can come to know why this wall has failed. Okay, so these are the references I have used in this presentation, and all presentations, all papers, you can get all this. My Google Scholar page and ResearchGate page. Also, sir has suggested me to brief those pages which I have used for this presentation, but somehow I forgot that thing. Just a moment. So here I conclude my presentation, and I'll be happy if you have any kind of queries related with this presentation. And that's why I have summarized my presentation within 80 minutes, so that 10 minutes you can have for any discussion. So over to you, sir.
Dear Vinay, thank you so much.
Sir, in the last part, I just quickly wrap because I wanted to save 10 minutes so that the students can have some queries.
No problem. I would first of all like to appreciate you so much for the presentation, because the influence of the relief shelves in reducing the earth pressure is really a matter which should be taken up, especially on the construction of taller walls. And you have made such an extensive study, starting from your physical test, then analytical models, then limit models, and finally wrapping up through a case study. It was really an exhaustive work, extensive thing you have presented. And many of the issues you have discussed and briefed very nicely, starting from the earth pressure distribution, the thrust, and especially the thing which you talked about, the moment. And the last words which you have put forward is really very important, that probably we don't know when it comes to the codes, because ultimately when it is not in the code, people doesn't want to follow in our regular practice. The thing which you mentioned, that it's not only about the stresses, but it's about the stresses and deformations, both have to be included. So the coupled stress deformation analysis, what we do, that is extremely important. So please accept my heartfelt appreciation for this extensive and elaborate presentation. I'm pretty sure a lot of new thoughts should be coming into the minds of the students when we move from the conventional teachings, and then when we look into the advanced research and things which are getting implemented in practice. So thank you for that. I open the floor for discussion, and if any students have any question, you are always now free to raise your hand, and you can have some interaction with Dr. Vinay. So Vinay, as I was mentioning, we have a student, Shubham Maurya. I think he is also from the same institute. You might have taught him. He was mentioning that 2 semesters he had been taught by you.
Sir, I might be knowing him by face because we do have a capacity of 156 students. So,
right.
I mean, remembering everyone's name is quite difficult, but definitely I'll be knowing him. Once I'll be able to see his face, definitely I'll be knowing.
We will see at the end. So students, if any students have some question, any query, anything you want to comment based on what you have listened, what you have studied, you can feel free to raise your hands. Yes, Devdut.
Yes. Hello.
Yeah, please.
Sir, my question is just like that. If we say that an earthquake hit in that particular area, according to the seismic zone, it hit the earthquake hit it. Like for that case, we have to consider the seismic forces also. In that case, when that structure, since we have built the structure according to the relief walls, I mean, the main part of introducing this relief walls is to so that we can just build the structure economically. We can just reduce its cost and all the stuffs, the concrete use. So that thing. So if the earthquake forces hit it and somehow the relief wall break, I mean, just partially or completely it broke. So suddenly the lateral thrust will increase. So since we have made such a structure which is not that much capable, I mean, for the conventional cases, we just make it according to the backfill we have. But since in this case, we don't have that much of good structure. So I mean, uh, do we have any precautionary measure regarding the same? I mean, if somehow that
Yeah,
thing breaks.
you have introduced a really very good question, because this is the question which has been many times asked to me during my PhD presentation. So what exactly is there? Whenever I presented my work over there, this question was asked to me in IIT Madras also. So what exactly is there? I just want to brief, because even I'm not pretty sure that how the earth pressure distribution will be there once seismic forces will be working. But what I can say, that I cannot assure you that how this wall will be behaving the seismic forces. What exactly is there? Seismic, whenever you are considering a seismic analysis, your forces is in the horizontal direction, not like this one. So there might be situation where such kind of wall might not work in the seismic, or might work in the seismic consideration also. Even very recently, I've been invited to collaborate. I mean, this is a foreign collaboration I have received from a professor, from Australia. They have asked me to collaborate on the same wall and under the seismic forces. I mean, behavior of such kind of wall under seismic forces. And once I'll be able to conduct some kind of study, then I'll be able to answer your question. However, you are saying regarding this crack and failure, definitely once this crack is introduced over there, even without this without the seismic force consideration, even in the gravity condition, this wall will be not be working. So you are right that if crack is being introduced over there, this wall will be definitely not good. But that's our responsibility, that we have to construct our structure in such a manner that it should not get failed in for the considered forces. So I think you got the answer or not, or anything else you have to say? Because I
Yes,
have
okay.
not done any kind of similar study. That's why I am just refraining my away from saying any word that how will it will be behaving. Because without doing any study, claiming any point is not a good thing. So anything else you want to discuss?
No, it's okay, sir. Actually, till now, whatever I have learned that, for the conventional structures, we just make the retaining wall according to the backfill we have. But this was the new thing that the relief walls was introduced in this class. So I thought that maybe in the factor of safety also, we should have considered the earthquake forces there, but you didn't mention anything regarding the same. So I thought that maybe, you must have missed it, but as you said that research work needs to be done on the same.
Yeah, that's a
So
good
it's
work
okay.
to be carried out. So if you are interested to carry out your research, and if you are willing to do this in area, you are most welcome to collaborate with me.
Yes.
Okay. Thank you, sir. Yes.
Okay. Thank you, Devdut. Any other questions from any student? So, Dr. Vinay, if I may ask one or two. Okay. Naveen, let him ask first. Naveen, please go ahead.
Yes, thank you, sir. So thank you for that nice presentation. So in one of the slides, you were showing the slip failures or the failure lines. In that, I could see two failure lines. One was inclined towards the wall and one inclined away from the wall.
Yes.
So usually in what we study is the failure line which is away from the wall. This towards the one incline towards the wall is, I think, new to me. So can you explain why that is formed?
I didn't get your question. Please, last line you just please repeat.
So the inclined one, like in the first top left figure,
Yeah.
the failure plane is inclined towards the wall, right?
Okay, what you have studied in, if you go for the convention, I mean, Coulomb's theory or Rankine's special theory. So what exactly is there? They have used a, wall only. Okay, no kind of base slab is over there. Okay, so what exactly is there? So your earth pressure, shear failure plane is being generated at the end of the wall. Okay, so that's why you are seeing this kind of pattern over there. But in the cantilever wall, we have witnessed this kind of shear failure only. So this is not applicable for the wall which you studied in the
Cantilever wall.
yeah, no, cantilever, simple wall. Okay, what
Yes,
you use
yes.
the conventional Rankines as well as this your Coulomb surface series. So even if you are if you are interested to learn this thing, so I'll just mention this thing. Once Rankine was carrying out this particular study, what he assumed that inclined backfill, and there he introduced a wall over there in between, and he named this as a rivet. Okay, and once he moved this away from the backfill, whatever earth pressure distribution was here, there, he called active, and it was based on the passive one, and there no such kind of base slab and all these things were over there. That is why in the wherever you book in books, you study this always starting from the base of the slab. Okay, and for this particular thing, you can refer the book by I'm forgetting the name. I'll tell Professor Arindam, and he will definitely communicate with the particular book where you can refer this kind of failure planes being happening in the case of cantilever retaining.
Actually, Naveen,
I just remember VNS Murthy is there. You can refer there.
Yes, exactly.
Okay.
Actually, Naveen, and for all the students, so whenever, as Dr. Vinay very rightly mentioned that when Rankine, Coulomb, these people worked, that time the concept of this base, stem, and heel did not come into practice in that way. So when you have this base point which is protruding inside the backfill, so it is also like a shelf. And whenever you have a shelf or any point of different materials of different stiffness contrast is protruding inside, so that time you will have a point of stress concentration from where the stress starts to dissipate. And that's where in these particular cases you will be seeing two different types of failure patterns which originates. One moving towards a stiffer material, one moving inside and through the less stiffer material. And that's what exactly we are seeing in this particular case. Even for the figure's bottom, you can see that one failure line is basically encompassing the base extension and the relief shelf, and then it is moving towards the ground surface. So it is following the stiffness contrast of the medium.
Yes. So because usually, as I remember in code as well, the failure line which is taken is from the heel in the same angle as we take for cantilever.
Yes, actually, as Dr. Vinay also rightly mentioned in the book by VNS Murthy and many other books also, whenever you look for the design of cantilever retaining walls especially, so you will always find that the height, when you basically configure the dimensions of the wall, the height of the stem is always configured with the condition of the backfill and the slip line which is generated towards the wall. Now, if your height of the stem actually exceeds and this slip line intersects to the stem of the wall, so in those cases we will have large amount of tensional distress in those cases. So that also gets taken care through this slip line inclined towards the stem of the wall itself.
Okay, thank you.
Okay. So I hope, Vinay, I told the right thing.
Sir, please ask me your question, sir.
Now let me see.
Okay.
No, I don't have question. I just have some because I'm also learning from your presentation only. So any question from any other student? Vaishnavi.
Yes, sir. Thank you for the very interesting presentation. I just wanted to ask, were pore water considerations done? Because in the case study, you mentioned that the wall failed right after the monsoon condition. So, like, was it considered in the analysis part done by you?
you have rightly said this thing. I have done this particular kind of thing study, which I have not presented in there, where I have done this particular study considering a clay backfill, where this pore water pressure distribution is always mentioned over there. There even we find that this configuration has led to fail with this wall. This paper is published. Even Sir was also there. We were there in a fifth. Forensic geotechnical.
Bangalore.
Bangalore. There is this paper. So on my ResearchGate page, you can get this paper. Okay, this consideration is over there. For this particular study, what I have shown, pore water pressure was not considered, but there is paper where pore water pressure consideration and all these things, completely submerged condition is also considered over there. You can have a look over there.
Okay, sir. Thank you.
Okay, any other questions from any other student? Okay, Dr. Vinay, I just have two specific queries. So when we do the physical modeling in the lab, right? So that time it is fine that we are actually laying the layers of soil, and then when we reach a particular height, we attach the relief shelf and use the glues to stick the sand and all those things we do in stages. But when we are doing in practice, so let us say any particular retention structure, whatever we are having is a RC structure, right? And that RC structure will be having these are monolithic only, I guess, right?
Yes.
Monolithically it will be constructed. So I was wondering, so whenever we will have this structure monolithically constructed with the relief shelves already present, the state of compaction, whether we can really achieve just at the bottom of the relief shells, it is very difficult, right? So how do we take care of that? Because that part, I think, again, state of compaction also guides a lot about the transfer of the stresses from the shelf to the soil or from the soil to the wall through the interjunctions. So how do we really take care of that in field, in practice? What is the notion in practice?
So what exactly is there that once I was studying this thing, we went to a site. This particular site was adopting this technology. What they told us that we are constructing in this stage manner. Up to once we are reaching the location of relief shelf, up to that we are backfilling. After that we are providing shuttering, and then we are constructing this relief shelf and pouring the concrete. Once this has completed, then we are going for further backfilling process. That's how they have gone. And sir, there is one Indian patent is over there.
Graviloft.
Graviloft.
Because
they have also suggesting the same thing, and that's how they are constructing. So sir, in very initial slides I have shown you, so they were just constructed in order to show the people that how they are constructing. They were not the exact
but you know, in a Graviloft I can still understand, because Graviloft is a there will be discontinuity and change of sections below and above the relief shells, right? Whatever you have in this.
Yes.
These are like rectangular sections at different heights that I can still understand. Constructing in stages is still not that difficult. But when we come to these cantilever or tapered retaining walls, right? Most of our cantilever walls are tapered, and then when we have the relief shelf, there I have a confusion, because in this picture also, in the Graviloft also, if you notice clearly, it is like there is one basal block, then there is a slab, and then there is another basal block. So it is not really in that way monolithic, what I understand from Graviloft as well. So it finally, when it is constructed, it looks like monolithic, but in a way it is not monolithic. Monolithic when we call it monolithic, the reinforcemental overlaps and the development lanes, those also has to be monolithically done, right? So so Graviloft, I understand there will be much greater tendency. So those junction surfaces will themselves be weak shear surfaces from the RC structure point of view. But what you were showing, right? What you were showing as a cantilever retaining wall with relief shelf, if what you mentioned that they are doing in stages, that way I can still understand. But see, in this case of Graviloft also, or in these relief shelf retaining walls, I am really concerned about the point of achieving the compaction state, if at all we are doing monolithically, just below the shelves. And if we are having one diagram also you are showing, right, there were some voids which were kept below the retaining wall. So whether those things also play a role. See, in numerical analysis or in our analysis, we can do all marvels, right? But how people will do it in practice, or whether what workmanship we will be needing for that to achieve the same compaction state, uniform compaction state throughout, those also probably has to be looked from a different perspective, right? So practice perspective we have to look into.
So even sir, this slab, I mean, what form work if we remove after once this concrete has, so there will be a space. Definitely, there will be a space.
Yes, yes, yes.
And what exactly we cannot do compaction over there. The only thing what we can do is that manually compacting something or manually filling up. That will be absolutely possible. Otherwise,
but, yes. So that's why I'm a bit concerned in the sense that what we always say for backfill material, that your backfill and wall backface, that should have good contact with each other. Otherwise, all our problem of transfer of stresses takes place, even though we make marvels in design. So that's where I was coming. In failure studies, right? In failure studies, we look from the perspective of the structural detailing or the geotechnical detailing, as you have showed us in your case study as well. But what they have actually done in the field during that backfilling, whether they are using a proper backfill material or they are just using some local soil, how they are compacting it, those also probably gets erased up once the system fails. So very difficult to assess those cases in the forensic studies.
Yes, sir.
So that's where only one concern I have with the how they would do in practice. That's the thing.
That was the same question we have during our this thing. That's why we have also visited this site, and there they have seen, and even we were not pretty sure that some gaps will not be there, because some gaps definitely will be there, and that will be also influencing how the earth pressure distribution will be changing.
Exactly.
Because the force transfer is definitely, if something vacant is over there, then it will be. But sir, I'm also surprised that the China people have made, because they kept every data very safe to them and we cannot access. But
workmanship, Vinay, workmanship, Chinese, Australian, European workmanship means I have more concern about the practical workmanship. I am not concerned about the design or the analysis. That we are doing marvels. But our workmanship means most of the failures when we look into forensic investigation, apart from your design and those things, we can always find some fault, always, because there is nothing universal. But what we do not look into the workmanship, what they have done, and we will never have those data. We never maintain those data. And probably that's a touch and go type of affair. Anyway.
Even, very recently, what happened, it is interesting to note. Because which is on the recording, so I cannot name this thing. What I did that in a structure which is a truss-based structure. So over the truss, we are using the nut bolt in order to tighten the truss with the members. So in that nut bolt, there is some washer thing is there, which will not let the water as well as air to pass. They didn't use this washer. Due to this heavy wind, this particular air has introduced into this hall, and the fall ceiling and all many things has been. So workmanship is always involved with this thing. And sir, regarding this question, even I will ask to the this person who is constructing such kind of wall, how they are doing, and if they can take a video of this thing, that will be
exactly. I was just going to tell that if a time-lapse video of that entire construction, starting from the shuttering and the basal construction, then rising above compaction till the end, if a time-lapse video can be made out of that, that will be fantastic just to see. But I doubt sometimes.
One additional point I just want to add over here, because the students are also over here, I suppose. Why they are increasing the width of relief shelf, there is a very crucial thing. Why they are increasing is the reason behind. If you see, sir, for this kind of wall, what exactly is there, that in conventional retaining wall, there won't be having any force which will be working downwards into the stem. But due to this kind of force, there will be a reaction, if you can see, sir. So due to this reaction, this particular member will be having a compressive kind of thing. And due to avoid such failure, they are thickening the sections.
Exactly. Actually, I was coming to that point also. Means see, because of the introduction of the relief shelves, which are again like semi-rigid RC structure only, RC shelves itself. So the intricacies in the reinforcemental layout also increases manifold. Now, whether they are doing those things properly or not, that is another question. So it might not be always just due to the design or due to the backfilling, that because the thinner shelves you have, the thinner shelves you have and the thinner taper you have, so more and more reinforcement gets overlapped and the percentage of steel increases. And when your percentage of steel increases, the spalling of concrete starts taking place very easily. And when this spalling takes place, that basically generates a crack. In the case study which you are showing, the crack was all along that shelf. So that's where I was getting some doubt whether the development or the anchorage length also was properly done or not. By design, it may be done, but whether in workmanship they have done or not. Because many a times we tell that, okay, 5 reinforcement bars will be passing through. But when 5 reinforcement bars is passing through when they're doing it in the field, if they're not able to pass through, many a times you will see they will curtail 2 bars somewhere and 3 will be put into. So those things are also a major concern, because the structure is now not so simple. As a simple cantilever retaining wall, it is not so simple anymore, construction wise.
So, sir, there is one point I can recall. In very beginning, sir, I told everybody that this kind of relief shelf will be perpendicular to the relief shelf. I mean, perpendicular to the stem. So that I intensely mentioned because what happened, sir, when I was in IIT Bombay, during the PhD, I was contacting so many contractors who are doing similar kind of structure. So a design which came to me, what I have noted, sir, what they done, if relief shelf is not this kind of having shape, they are having this kind of shape. Upper surface is horizontal and lower surface is sometimes this thing. I think they have prepared so that the backfilling can be done properly, as well as the joint has been. Joint should be somewhat rigid one, so that's why they are increasing the thickness near the joint, or also making it slow so that backfilling will be very easy. So what the point you have raised is
that might be helpful. Yes.
Yeah. Yes, sir.
That might be helpful because once you have that inclination, even the soil, putting the soil below is much easier, and upper portion anyways will be filled up.
Yes,
that's correct. That will be helpful. Okay, Vinay. So very nice and elaborate presentation. Thanks a lot. A lot of things to learn.
Students have also participated in the question and answer round, because many times we have seen that we deliver, but students don't ask the question. So once students are asking, that means I'm pretty sure that they were listening very sincerely, and that gives satisfaction that whatever we have delivered, students have listened. And I can say my day was fruitful.
Exactly. Actually, this batch is very interactive. I'm pretty happy with this batch, the way things are going on. So
thank you, sir, for me having up.
Thank you. So before we disperse, we will have our traditional group photograph through the Teams itself. So if you can now unshare the thing, Vinay.
Yes, sir. Okay, sir. Just a second.
And if you can share the PDF of these slides, then it will be beneficial for the students.
PDF of this slide, sir?
Yeah.
Yeah, I can share, sir. No issue.
Oh. Okay. So now you can stop sharing and let us all.
And other portions I'll give you.
And I'll request all of the students to switch on their camera. Okay, this one I will take. Okay, Vinay, now you can stop sharing the slide. We will take a group photograph with everybody in the video mode. Okay. Okay, we'll just wait for a minute, let others join. Okay. Still people are joining. We'll still hold Vinay for a moment. Okay, so requesting everybody to give up your best smile. I'll take one more. This will be more like a classroom sitting. So I'm seeing quite a less number of video cams. Others are there or not. Okay, let me take this one. Okay, fetchies. Okay, thank you. So thank you, Vinay. Thank you so much for today.
So should I leave, sir?
We will all disperse then. If anybody else do not have any further question, then we will all leave. Okay, thank you, Vinay. Thank you for very nice presentation, nice interaction. Lot of things you have conveyed to the students, and from all of our sides, we give you a heartfelt appreciation for your presentation.
Thank you, sir. Thank you for nice. Thank you, sir.
Okay. Thank you, students. So
Thank you, sir.
Okay.
Thank you, sir.
We'll meet.
Thank
Goodbye.
you, sir. Thank you, everyone. Thank you.
Bye.
Thank you, sir.
Thank you.